All right, for lesson 21 today, we're going to look at, first of all, I'm going to continue with the Highland craft store problem and talk about an interesting kind of constraint that you'll need to be aware of and familiar with to see how these things can work. And then we're going to go into two more formulations. Each have some interesting twists and ways to look at these linear programming problems. So the first problem is going to be the seaboard trucking problem. And then in the next lesson, next video, we'll talk about the Mystic Coffee problem. They're classic linear programming problems, classic in the sense that they have a particular form that's useful, and we'll see how that works. And then the seaboard trucking problem is a transportation problem, and then the Mystic Coffee problem is a blending problem, and we'll see how those things work. So let's go ahead and dive in and begin with talking about again our Highland craft store problem. And of course, you remember this. We're maximizing our profit, $40 for each bowl and $50 for each mug. And of course, we have the same constraints on labor that it has only 40 hours, and clay, we only have 120 pounds. And of course, we have to produce a positive number of or zero bowls and mugs. And given this information, we know that our solution value lies at the intersection of the clay and labor constraints, and that this would require us to produce 24 bowls and 8 mugs. But suppose we take that solution to the store owner, and the store owner says, well, that I appreciate that, understand, but what I want you to do is, because of the way the sales go, I want you to be sure to produce twice as many mugs as bowls. So now the question is, how will you accommodate that? So the first thing I'd like for you to think about is this is a new requirement. What if Highlands Craft must produce at least twice as many mugs as bowls? So that's a new requirement. And anytime you think about this and you have a requirement, then that really is the way this is going to be handled is this is a constraint. So we need to consider how to deal with this, because it's a new constraint. So now, how do we do that? Well, of course, first of all, we have to translate this into an algebraic statement. So let's take a look at this on the next slide. So we must produce at least twice as many mugs as bowls. And of course, we want to remember that the number of mugs that we make each day is represented by the variable m, and that's just a number, a letter that stands for a number. And of course, b is the number of bowls. All right. I think that you would understand that right away there's a relationship that needs to be satisfied between m and b. And we know that the mugs has to be greater than, and I'm going to just write greater than, and of course we'll know that includes, anytime I write greater than, that includes the equal to. So the number of bowls has to be greater than, number of mugs has to be greater than or equal to the number of bowls. But then the question becomes, what do we do with this twice? I know in your mind that indicates somewhere in this inequality there has to be a 2. And where does that 2 go? Does the 2 go in front of the b, or does it go in front of the m? And your intuition will tell you And in this case, in almost every case, your intuition is going to be wrong. So be careful. The intuition is going to tell you to put the 2 in front of the mugs. And so the relationship then would be 2 times m is greater than or equal to the number of bowls. But if you do that, unfortunately, you're going to be wrong. That's not correct. Okay, so the question then becomes, what is correct and why? Well, let's think about this. Let's suppose, and remember, what's the definition of a variable? So if the definition of a variable is just a letter or a symbol that stands for a number. So rather than rather than using b, let's use an actual number. Let's suppose you make 1 bowl, and if given this requirement, at least twice as many bowls as mugs, what then will m have to be? Well, then m has to be, hopefully you can see that m has to be 2, it has, or 3, or 4, and so forth. Something larger than or equal to 2. Okay, so here's where the insight comes in. In order to make that happen, we already know that, first of all, that this relationship has to be greater than, the number of bowls has to be greater than or equal to, number of mugs has to be greater than or equal to the number of bowls. But the 2 actually goes in front of the number of bowls. Then so this says, anytime, if for example, we made 1 bowl, then that means that the mugs would have to be greater than or equal to 2 times 1, or greater than or equal to 2, which is exactly what we want to have happen. And so the correct relationship is this number. The correct relationship is m is number of mugs is greater than or equal to 2 times the number of bowls. And so that's the correct relationship that we're going to, and of course I don't want to forget, because it's not strictly greater than, it can be equal to, so it's greater than or equal to 2 times b. So now then the question becomes, how does this then apply with respect to our solution? And what requirement, what does it, what happens to our solution? So we're going to explore that a little bit on the next slide. So you remember, this is our previous problem with 2 constraints. And now we have a third constraint that we need to add, which is that m is greater than or equal to 2 times the number of bowls. Now this can be written in any number of ways. It can be written as m minus 2b is greater than or equal to 0. It can be written also as minus m plus 2b is less than or equal to 0. It can also be written as 2b is less than or equal to m. Any of these relationships are equivalent. But the question is, we need to plot this constraint on our graph. And how do we do that? Well, here's again, we need 2 points that will satisfy. Let me police this up a little bit, because this is strictly greater than or equal to, less than or equal to, less than or equal to. Okay, so now how do we plot this? Well, before we tried to get 2 points to make a straight line, and we can do that here. The only issue is, in this case, if for example, if b equals 0, if b equals 0, then what's m? Then you'll see b times 2 is 0, so m is going to be also equal to 0. So interestingly, this constraint goes, this is 1 point on our constraint, the origin, 0, 0. So this is 1 point of our constraint line. So then the question is, what's another point? So let's pick another point. Let's just let b, let's let b equal 10. And if b equals 10, we know that m equals 20. It's twice as many. So then we'll have the origin and 10 bowls and 20 mugs. So here's another point on this line. So then the constraint line goes through, it should go through those 2 points. Let me try to do that a little bit better. Through the origin. Hard to draw a straight line. Anyway, let me try one more time. Let me go this way from this point down. That may be a little better. In any case, we've got this cuts our, if you will, it cuts our feasible region into 2 pieces. First is a triangle here, and let's just call that piece number 1. And then the second piece is this polygon, and that's piece number 2. So the question is, if this constraint line runs through these points, what happens to our feasible region? Well, first of all, either the area number 2 is going to be the feasible region, or the area number 1 is the feasible region. And the question you need to ask yourself is, which side of this line satisfies those constraints? And so if you would just pick a point, any on either side of the line, and determine whether or not that point satisfies that constraint. So let's take a look. Let's pick this point here. And if you'll remember, the constraint is m is greater than or equal to 2b. Okay. So let's see what m is. First of all, you'll see b is 0 and m is 10, 20, 30. So 30 is definitely greater than or equal to 0, 2 times 0. So we know that 30 is strictly greater than 2 times 0. And so it does, in fact, that satisfies the constraint. So we know that this triangle, section 1, satisfies the constraint, and section 2 does not. So let's go then to see what this really looks like in a better representation. And so now we're back to, we've added our constraint. Here's the new constraint. And we know that this triangle area that we called 1 is the feasible region. So now, given our objective function, what's the optimal point? And if you can visualize this, if this objective function line lies outside of the feasible region, so if you visualize moving this line back down this direction until it first touches the feasible region, hopefully you can see that it's going to touch the feasible region at that point. So this point where our new constraint and our labor constraint intersect is now the new solution. Let's see if we can work through that. We're going to do that same process of solving these equations simultaneously. What you'll learn is, let me see if I can type this in quickly. 2b minus m is going to be equal to 0, and our second constraint is our labor constraint, and if that's b plus 2m, oops, that's the wrong symbol, plus 2m equals 40. So we need to solve those simultaneously. And what I'll do here is, first of all, let's multiply. Let's do this a little bit differently. And in this case, let's try to eliminate the m's. And the way I would do that is I'm going to multiply this first equation by 2 because I want to eliminate the m's. So then that equation becomes 4b minus 2m, 2 times 0. It's still going to be equal to 0. And we add that to the previous equation, and you'll see 2m minus 2m goes away. But that leaves us with, now we're going to add b plus 4b, and that's 5b then equals 40. And so we'll know, we can see right away that b equals 8. And if b equals 8, we know that we can then substitute that back in the first equation. And if b is 8, 2 times b is 16. 16 equals m. So the new solution is b equals 16, m equals 8. Kind of got that backwards. B equals 8 and m equals 16. Okay. And then you can substitute those values into your objective function and determine your new optimal solution. That's 40 times 8 is 320. 16 times 50 is 800, so that's $1,120. And so you can see that that will have cost us some profit. And you can take that back to your boss and say, well, we can do this, but it actually is going to cost us profit. Okay. A couple of things I want you to notice. Number one, anytime you add a constraint, the feasible region either gets smaller or it stays the same. It can stay the same. For example, if we added a constraint, that fell like this, it would fall outside. So anytime it it falls. It's either the feasible region will either stay the same size or be decreased. It'll never increase by adding constraints, which is, interestingly, it's common sense. The more constraints you add, you cannot increase it will certainly, it decrease or keep the same the number of possible solutions that you have. Okay, so let's look at the next case. And I'm going to leave this to you to determine, but what happens if now you go back to your boss and say, oh, well, I meant to say that we need to make twice as many bowls as mugs. That's actually what I meant. Well, if you go through that same logic, you come up, this will generate, and I'll leave this to you as an exercise, and it would be a good exercise to go through. This is the new constraint, and it turns out that the feasible region now is below this triangle once you add the constraint in. And if you might imagine, you'll notice that the optimal solution lies right at this point. And that shouldn't be a surprise, because as you bring your objective function back toward the feasible region, it will first touch that feasible region at this point, which was our initial optimal solution. And just remember, what was our initial optimal solution? That we had bowls was 24 and mugs was 8. Oops, 8. And if you'll notice, certainly our bowls, we've made twice as many bowls as mugs. We've made 8 mugs and we've made 24 bowls. So that satisfies this, certainly satisfies that constraint, and as it does. And so the feasible region, even though it gets reduced, the optimal solution stays exactly the same, and you'll have $1,360 profit. Right? Work through that as an exercise. And now we're going to go on to another problem.